Okay, let's get started. So, yeah, I will present the new cryptographic accumulator that I recently interested in, which is published in ePrint called the Dynamic Universal Accumulator with Batch Update over bilinear groups. This paper is authored by Joseph and Alex. We usually call it the VB20 cryptography accumulator. So I first introduced some basic concept about cryptography accumulator. So a cryptographic accumulator is held by an accumulator manager, which allows to aggregate many different values from a finite set into a fixed length digest. We call this value accumulator value. So users can use the public key of the cryptographic accumulator to verify if an element is accumulated given the accumulator value by using some value called membership witness. This membership witness is issued by the accumulator manager. So the accumulator manager can add and delete elements from the accumulator as well. So this step we call it the accumulator updates operation. If the cryptography accumulator protocol supports both addition and the deletion operations for one or multiple elements to or from the accumulator, we call this accumulator protocol supports batch additions and deletions. So once accumulator updates, already issued witnesses should also be updated consistently to continue verifying the validation of the witness. So this step we call it the batch witness update. Also, the accumulator protocol also needs to support zero knowledge proof of knowledge protocol. That means users can use their witness to prove the ownership of a valid membership witness for some value with respect to the current accumulator state. So let me give you a high-level elaboration of the accumulator protocol. So the first step is that basically there are two roles of in this protocol. The first role is the accumulator manager. The second role is the user. The accumulator manager is a kind of like a trusted third party. It can initiate the accumulator using some initial elements. Here, for example, I use a 1, 2, 3, and all elements are represented by strings. And we hash each element and combine them into an accumulator in some sort of algorithm. The accumulator can be taken as a hash value, mean hex string. This accumulator is also initiated with the secret key and public key pair, and the secret key is held by the accumulator manager, and the public key is published to all the users in the verification step further. So once we have initiated the accumulator, the manager can issue witness to users. For example, the manager can issue a membership witness associated with value 1, and the user can use the membership witness and send it to some trusted party. The trusted party is trusted by the accumulator manager, and the trusted party can use the public key and the membership witness and the current state of the accumulator to verify the validity of the membership witness is output true or false. Also, the accumulator protocol supports the update operations or batch update operations. That means You can update the accumulator by adding some values and delete some values. Here, for example, we add new values 4 and 5 into the accumulator, and we delete the element 2 with element out of the accumulator. Then the accumulator value will be changed to a new hex string. We call this step is accumulator update, and the state of the accumulator is changed. So once the accumulator changed, the user also need to update their membership witness in some sort of algorithm, and so that the user can continue using the membership witness updated, and to send the witness check to some trusted party, so that this value can be still verified by the trusted party using the same public key and the updated accumulator and updated membership witness. So the last feature of the accumulator protocol is that the user can prove in their membership using zero-knowledge proof of ownership of their membership witness. That means using zero-knowledge proof, he don't need to reveal the secret of the membership witness, and you don't know which value the membership witness is associated with. You can just send the zero-knowledge proof or ownership of valid witness to some trusted party, and trusted party can verify true or false. And some notice to these slides is that the VB20 protocol also supports non-membership witness methods, but that is not in the scope of these slides. The reason is that the first reason is that the non-membership witness methods has more strict conditions, and is way more complicated than the membership witness. And the second reason is that in my project we don't need non-membership witness for now, so we choose to skip it. And if you are interested in, you can sketch the paper and get into details how it works. So let me continue to introduce how the math underlying of the protocol. So this protocol is based on the bilinear groups parameters. You can use the BLS 1, 2, 3, 8, 1, G1, G2, GT groups, and the scalars are over finite field FQ. Q is the order of the field, and the P, we denote the P and the P prime are generators of G1 and G2 respectively. The accumulator parameters, the secret key is just a scalar, the random scalar from the finite field FQ, and the public key is the secret key times the group generator of G2. So to initialize the accumulator, you can initialize the accumulator with just the generator P, or you can denote the initialization of the product of yi plus secret key. Multiple yi is like the 1, 2, 3 elements that are initiated in the example. So to update the accumulator, if a single update, you just need to time the current accumulator with 1 plus secret key, and to delete, you just need to divide y plus secret key. So to issue a membership witness is just the current state of V divided by the y plus secret key, and the accumulator manager issues this to user, and user can use it to prove that y is accumulated into V. V is the current accumulated value, and YV is the values accumulated, and those values are only known to the accumulator manager and not published. So to update the witness, this is again, this is just for single update. You just need to add the element. You need to update by computing y prime minus 1 times w plus v, where y is the new value. Y prime is the new value and y is for all values in the current element. And the delete, you just need to 1 divided by the y prime minus y times w minus v prime. To verify is very simple. A member should witness w for element y is valid for the accumulator v if and only if the pairing succeeds. And the witness verification is very simple, and you can just use it as a smart contract program and write a program to verify whether the verification is useful. And this is also useful in the blockchain setting because you can write a smart contract to verify it. You don't need to know who is the verification and who is the member of the blockchain network. So accumulator batch update is way more complicated, and this is how it works. The accumulator batch update is given 2 sets of elements that to be added and deleted. We call it YA1 and to YAN. And the deletion set is the YD1 and YDM. And this there's no intersection between these 2 sets. And to update it, we need to compute these 2 polynomials, DA and DD. Then we compute DA on input the negative secret key of DA and the negative secret key of the DD, and divide DA divided DD and times V. To batch, accordingly, we need to batch witness update because we changed the state of the accumulator, and this step is way more complicated because for some polynomial operations. So to update the witness, you just need to compute some new polynomials VA, VD, and VAD. That means you can compute DA divided DD on input Y and times W plus VAD divided by DD times V for each Y. And where W is your current witness and W prime is your new witness. Some problem of this step that attracted my attention in the paper and I feel it's very interesting. Recall that we compute VAD divided by DD on input Y. The problem here is that the users cannot batch update their witness immediately using the formula VAD. This is because using computing the VAD, we have to know what the secret alpha is. Alpha is the secret key. So we cannot publish how we calculate the polynomial because we have to publish the secret key. So that's the problem underlying of the method of this protocol. So the solution of this problem is that the accumulator manager just publishes a vector of coefficients of the polynomial of VAD divided by DD polynomial, and let users evaluate it on Y instead of publishing the secret key. And this step, there's an argument in the paper, so there are more details in section 4.1. And if you are interested, you can go through that. Also, this protocol also supports batch fitness update among epochs. For simplicity, this feature is just a means you can do multiple batch update. That means it not only permits users to batch update their witness from the previous accumulator state, it also enables them to directly update from any old accumulated state. For example, in the blockchain, you don't need to know what's the previous state. You can just use the first block and you can update to the current block. So there are more details in 4.2, and the idea behind of the batch fitness update among epochs is very similar to the batch update, but using one new polynomial, you can just do one more polynomial instead of do the batch update multiple times using the batch update algorithm. Also, it also supports ZK proof. The protocol is very straightforward. It's just to use the failed Shamir transformation as a non-interactive proof of knowledge. This is clearly described in section 7. And notice that in section 7, they also just describe the methods for the ZK proof for non-membership witness. But it's very easily to be adapted to be a membership witness ZK proof.